am going to do Combinatorics for you guys this week. So our first lecture is going to be a bit more of a fun one. We're going to do some tiling and some game theory. So we're going to start with the first example, which is on the board. And we're given basically a standard chessboard, but we've removed two of the corner squares. So black square there and a black square here, two opposite ones. Hey, please go sit. Okay. Can anyone tell me whether it would be possible to cover this by 2x1 squares?
No.
No. You say no? And the girl behind you? You also say no. Okay, do you have a general suggestion, strategy to show how it's not possible?
You count the amount of black squares and white squares, and you find that there are 30 black squares and 32 white squares. And each domino covers one black square and one white square. So the amount of, because the white squares and black squares are not even, you can't cover the entire chessboard.
Okay, so exactly what he said. In this case, it's quite nice because they already tell us it's a chessboard, so we already know we have black and white squares. So you basically, like he said, you count the amount of black squares. And you see, because you remove two, there's only 30 black squares. And if you count the amount of white squares, you'll see there's 32 white squares, right? But if you want to place basically a domino piece, which is a 2x1 square, it doesn't matter which orientation you place it. If you place it like this, it will cover both one white square and one black square. If you put it in a different orientation like that, it will again cover one white square and one black square, irrelevant of where on the board you place this piece. So it means that every time you place a square, you will cover one white and one black, which means the amount of uncovered squares will both decrease by 1. So you'll go all the way until you've covered all the black squares, but there will still be 2 white squares left, which you can't cover with one domino piece, because the domino piece will be on a white and a black square.
So what about if we went to 1x3 or 1x5, does dimension then come into it?
So then the question definitely changes. So our coloring, which is now chessboard coloring, we call it, which is this diagonal white and black, will no longer necessarily be useful in that case. So if it's 4 pieces, it would, if it's 4x1, it would still work because you're still covering 2 white and 2 black. But when it's 3x1, for instance, like that, it would no longer be useful because you're covering 2 black and 1 white, or you could place it like this and then you're covering 2 1 and 1 black. And then you can't automatically, just from this coloring, say that it's impossible.
But couldn't it also be impossible because the amount of tiles on the chessboard isn't a multiple of 3?
Okay, in that case, that would be your immediate, very easy. Well done, your nice argument. But for 5, okay, 5 it goes the same. You could go up in the numbers and see what works and what doesn't, but for 2 pieces and for 4 and for 6, this is a nice argument. But if you have a number that divides 62 and it covers an equal amount of white and black squares, you'll have to resort to a different coloring system. Okay, so we call this background basically that we colored in, this alternate white and black squares, our coloring system that we are using. So this is chessboard coloring. Okay, all right. No problem. Just find a seat. so this is similar to what you asked when you have bigger pieces. In this case, we also have a bigger board because 8 by 8 would be trivial in this case. That's very ugly. Sorry. Okay, can anyone tell me whether this will be possible or impossible?
No.
No, impossible. And at the back, you agree impossible. Okay, any suggestions about coloring systems that might work? Let's start at the backs this time. No? Okay, front?
You can use 4 colors and color them diagonally.
Okay. Why did you choose 4 colors?
Because if you choose 4 colors and you color them, because it's a 4x1 piece, it won't really work with, because if you use the black and white one, it will be possible because they always cover the same amount, 2 white and 2 black. And if you use black and white, then there'll always be 50 black squares, 50 white squares. But if you use 4 colors and color them diagonally, you'll find that there are not an equal amount of each color, and with a 4x1 piece, it will cover 4 different colors, any orientation you put it.
Okay, so what his point is about this system where we only use 2 colors is if you place a 4x1 piece here, you'll still cover 2 white and 2 black, the 2 of each color, but this whole board will have an equal amount of both colors. So if we use that same coloring system, we'll have 50 white pieces and 50 black pieces, and we'll place pieces that use 2 white and 2 black at the same time. So it won't tell us anything about the coloring system. So the important thing just in proofs like this is either to prove that it is possible, you need to actually go draw the construction of how it is possible. So you need to take this board and you need to draw 4x1 pieces on this board, the whole board, to show it is possible. To prove it's impossible is why we are using the coloring systems. So the idea is to find a coloring system where the pieces cover certain amount of colors and the number of pieces of that color on the board doesn't match. And that's to prove that it's impossible. So he said that for a 4x1 piece, he chose 4 colors because, well, 2 colors is just not enough in this case, or for the way he wants to do it, because, as we said, it doesn't prove anything. So he chose 4 colors and he suggested a diagonal coloring. So it's similar to that in a way, but you're going to color like diagonally, and go like this, and all the way to here, and then you're going to take the next color and you're going to go that way, and the next one, and then so you'll keep on black, blue, red, green, and something on this side will be green again. And then red. And so you'll keep on coloring this whole board. So you color the whole board in those colors, and then, as we did in the previous question, you go check how many black squares there's there, white squares. So in this case, how many black, blue, red, and green squares are there. So the case why it won't be the same is because this black is on the longest diagonal, and like the blue is on a smaller diagonal, and the red on a smaller one. So when you add it all up, it won't be the same. So you have the black, there is 30. The green is also 30. Ooh, I probably colored mine differently. Sorry. 26. There we go. And then green. And 25, I believe. Black, green, red. 24 and blue. It's 25. Oh, sorry. Okay. So we see that there is not only just different, but they're all a bit different, and it's kind of strange, the numbers, but it helps us in this case. So, like he said, when we check out how we will place a piece, 4x1 piece, it will either be horizontally or vertically, right? So if it's horizontally, it will look like that. And if it's vertically, it will look like that. And you see that in both of them, that piece covers one of each color. And it doesn't matter where on the board, if you put it here, if you put it there, no matter which way, it covers one of each color. Okay, so it means, again, like we had there, these colors, if we put a piece down and we cover one of each color, these numbers will decrease by 1 every time you put a piece down. If we consider this to be the uncovered number of squares of each color. So it decreases by 1 every time you put a piece down, and so it goes on. So in the end, we'll run out of red pieces, but we'll still have the other colors left. And then we'll see it's not possible. So this is a nice coloring system to use to prove that we can't do this. But why is this one specifically unique? Well, it's not. You can do this in quite a few other ways as well. So, can anyone find me a different coloring system that proves the same example, that it's not possible? I'll give you a moment to think.
Oh, you just go in like a rose, so like a black rose and a green rose and a red rose.
Okay, great. Let's try that.
Oh no, sorry, that one not.
I mean, you suggested it. We'll try it. This is maths. It doesn't necessarily need to work for you to try it. Okay. Almost done. Okay, so you said make the first row black. Then the next one blue. Green and red, right? Okay, cool. We'll see though that, again, we're gonna do black here. Black, green, blue, green, red, black, right? And similar to this color, blue and blue, green and red. Okay, so you see here that now we have 3 black rows and they're 10 each, so we go count it. Black, there is 30. Blue, there is also 30. Green and red, there's both only 20. Okay. Right. So why did you think it might not work?
Because the black and blue are both like so much more than the green and the red, and so it will give like an inaccurate representation. So black and blue together give 20 more. So you're gonna cancel out all the greens and reds and the 20 from the black and the blue. So you'll have 10 left from the black and 10 left from the blue. But then you don't have any other colors to cover. But if you actually place the tiles there, you can do it, but it won't work with this color.
Okay, we can chat about that, see where it goes. Yes?
Because you can place on only one color.
Yes, so that is also, so what you were talking about, you only considered that we might place it vertically where it covers one of each color. but you can also place it horizontally where it kind of covers four squares of each color. So you can, all black, all blue, all green, all red. But I mean, the way that you suggested it, if we do 20, that's vertical, then you have 10 here and 10 here, and you can't exactly fit them into 4. But how do we prove this? How do we state it? Okay, so are you familiar with mods, modular arithmetic, in any sense? Who has seen it before? Okay, a few guys. So the idea of modular arithmetic is that you divide it by a number, and then you see what is the remainder after you divide it by the number. So if you have 15 and we want to divide it by 4, then you say 4 goes till 12, 4 8 12, so that's 3 times 4 is 12, but you have to add 3 to 12 to get to 15. So you would write that 15 is congruent to 3 mod 4. Okay, it's a very weird way of writing. You'll definitely still learn about it this week. But the idea is you divide by a number and you see what's the remainder. So in this case, we have pieces that are of length 4, right? So let's take our numbers here and we divide them by 4, okay? So we see that if you divide 30 by 4, it only goes till 28, and then you have 2 left, right? So 30 is not divisible by 4. Okay? See you frowning. Does it make sense?
No, I'm just confused.
Okay. Any questions about that? You'll definitely go into more depth about this, yes?
Could you just quickly re-explain what mod is?
Okay. I don't want to cover it completely now because you'll see there's a lot in algebra and number theory. Okay, so you divide by a number. So in this case, we're going to divide by 4, right? And you see, when you divide by that number, what is the remainder that's left? So if we take 30 and we divide by 4, 7 times 4 is 28, right? So if you want to write it out a bit better, you say 30 equals 7 times 4 plus 2. Okay, everyone happy with writing it like that? And that's basically what you do with mod. So we care about this 4, because we want 30 to divide by 4, and we see that this is the remainder. Okay, so basically all we care about is the remainder in this case. If you took 40, you would see that it's 10 times 4, so there's no remainder. If you take 50, you see it's 12 times 4, which is 48 plus 2, and then that's your remainder again. Okay. In this case, why we care about whether these are divisible by 4 is because we can place tiles in the sense that they cover 4 of each color. Okay? Any further questions so far? Okay. I'm just going, okay, so if we divide 30 by 4, it's 7 times 4 is 28 plus 2. So our remainder here is 2. Okay, so I'm just going to write a 2 there. Another 30 is still 2. 20 is 0 because 20 is 4 times 5. There's no remainder. And the other 20 is 0 as well. Okay. Does the mods work a bit, or is it?
You're going to write the mod bit.
I could definitely, as long as the notation doesn't scare you off. Yes?
There's a 4 there, but there's no 5 or 7 there. Then how do you know that it's a 5 or 7? If it's like a giant number, you have to find it.
I say again, where do you want there to be a 5 or 7?
So like, how would you know that 30 is 4 times 7 plus 2 if there's no 7 there? Because you only wrote the 4 and the 2.
So we don't care about which number it's multiplied. We only care, so that's why every time we care about the remainder and the 4 that you're multiplying it with. That's why all of these numbers, we go write them in terms of something times 4 plus a remainder. And we don't really care about the something for now. Okay. So, when we place a piece on this board, we either decrease, we either place it this way, and then we decrease each of these numbers by 1, or we place it this way, and we decrease one of these numbers by 4. Right. So a rule with modular arithmetic is if you change something by the mod that it is there, it stays the same. So if you would subtract 4 here, it would still be equal to 2 mod 4. So with modular arithmetic, if it's that number that you're subtracting or adding, or subtracting or adding any multiple of 4 here, it would stay the same. Because it's, for instance, if we take 30 and we minus 4, then we get 26, right? Okay, 26 is equal to 6 times 4 plus 2. So the remainder here did not change from what we had there. And then similarly, if we take 30 and we add 4, which is 34, which is equal to 34, it would be 8 times 4 plus 2. Again, the remainder is 2. Okay, rather maybe come back to this way of proving it after the modular arithmetic is stuck a bit better on. It will definitely make more sense. But for proving this coloring system, we see that either we subtract 4, which doesn't change this number at all, or we subtract 1 from each, which decreases this number of all of them by 1. And the point is, for us to cover the whole board with 4x1 pieces, we need all of them to be 0. All of those numbers to be 0, which would mean all of these numbers would be 0. But we can't do that if we can only subtract 1 here, 1 here, 1 here, and 1 here, because then none of them, well, in this case, if you subtract 1, none of them would be 0. And if you subtract 1 again, they would be 0, but they won't be 0. And you'll continue on in this cycle. So using this way of just describing both ways you can place it, you'll see that it's not possible with this to place a 4x1 piece on this board. Okay. One more possible. Can anyone think of any other way to do the same problem? I mean, we had color rows now, which is similar to doing columns, so we're not going to do that one. We did some diagonal placings with 4 colors. Any other rough guesses, random sparks of creativity? So up to now, we said that we're using 4 colors because we have a 4x1 piece, right? And that was a very good mindset to have. It worked very well twice. But is it possible to still use only 2 colors for this? Because, I mean, you could have a very long piece, like a piece of length 10. And are you going to use 10 colors then if you try to do this? Yes?
I think it should work. Because if you use the chessboard one
Mhm.
and you divide them both by 4 into that mod thing, they'll both have remainder of 2. Because it's 50-50 and you divide it by
50?
4, you'll get 48 for both.
Yes, and okay, great. Then you get a remainder of 2, and every time you place it, it's 2 of each. Yes, so that's perfect. That would actually be a great one. So he just said if you use the chessboard, again, you would, yes, on this one, you would have 50 black, 50 white, and then if you do it mod 4, you would have a remainder of 2 for both. You could quickly just write that down as well. So you would have black as 50, we would have white as 50 as well. And this is, as we said with our mods, this is mod 2. We're taking it for base 4, right? And every time you place a piece, a 4x1 piece on this board, it would cover 2 of both, right? Just thinking for a moment.
But isn't that 2
Yeah, no,
into
this-
50 and 2 into 50 though? It does go.
Say again?
Well,
If we,
you're not. It's not 4. It's not a set of 4. It's 2 2s.
yeah,
So the
it's
two,
gonna,
the two black or blue, whatever that is,
Yeah.
black would go into
Well,
50. So is that
yeah.
a valid argument?
no, I'm thinking now because you're not reducing this by 4, because in this case we were placing a piece on all black, so it was all 4. In this case it's only covering 2 black, so it's going to be -2. Sorry, but nice try though, and it was a good attempt. But if we do go back to the chessboard and we do think about that, yes?
Well, instead of making blocks, why are we making blocks of 4?
If we make blocks of 4. Do you mean like chessboard but with 4 blocks? As in making, we started there was white, but let's start with black. As in that, as a chessboard, and then, I mean, let's go for it. So this is basically, again, our chessboard coloring, but just a bit scaled up. Okay, so, oh, that's a very rough sketch. Sorry about that. In this case, let's see. Our black blocks, if we look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 black blocks of all size 2, right? So our black squares is going to be 52, and our white squares is going to be 48, right? Because it adds up to 100. Okay, my sketch isn't too rough for anyone. Okay, and in this case, we are going to, again, any piece that we place will cover 2 black and 2 black and 2 white squares. Place it like that. 2 black, 2 white, place it like that. 2 black, 2 white, place it like that. And similarly for all the vertical faces as well. Yeah, that would be, there it would be, okay. Any way that you place it on the board, it will cover 2 black and 2 white squares. Meaning, similar than what we had above there, we have, every time it's the same amount of black and the same amount of white. But for this coloring system, there's not an equal amount of black and white squares. Meaning, you'll place a piece, this will reduce by 2 and this by 2. Again, place a piece, reduces by 2, reduces by 2, and you go on like that. But in the end, you'll have covered all your white squares, but you will have black squares left that you can't cover with a piece because it is both on white and on black.
Are we still using, I've lost track a little. We're still using a 4x1.
Yes.
How are we covering? So, so you could be covering 2 black and 2 white. Or you could be covering 1 white and 3 black.
No, so you can only cover 2 black and 2 white. Because in all these positions, which is basically some of, in any place that
okay,
you put
yes,
it.
yes, so,
Yes.
yes, correct. Fine.
It takes a moment to
Yeah.
to think about it. Okay, and then we see again that this is a very effective system of proving, and in this case you only needed 2 colors. So you don't always have to go for the amount of colors, but it clearly worked well also. Okay, great. So, right. So now we know that the only way of, if you want to prove it as being true, you have to actually draw it, take the diagram and draw the pieces on it to show the way that it is possible. To prove that it's impossible, a coloring system is always a great idea. So the coloring systems we did now is we had some rows. You could also do columns. We had some diagonal ones. We had a chessboard one. You could even have a bigger chessboard one. There's some weird systems as well. You could really try anything, as long as there's maybe some link to the piece you're trying to put on a board. You could also, if you have some strange type of board, do something in the line of, I'm just going to maybe make the corners one a specific color and then the in-between ones a different color. There's quite a few systems that like this that also works. I will put in, and then inside you can either go on with the X's, which sometimes works as well, and put different pieces here. There's a lot of strange things, and a lot of them actually works very well. So this is just a very random example, but I'll look for an exercise that uses a nice coloring system like that for you guys. Okay, so just the important steps when you do try to prove it impossible in this case. Go physically draw the coloring system on your page. If you don't have more than 1 or 2 colors, you can use X's and dots as well to indicate different colored squares. Write down the amount of squares, black this, white this, whatever your color is, and write down the amount of squares that one piece will cover. So you need to write all of this and then explain why there's a contradiction and why it won't work. Okay. Great. Okay, the next example, and this is going to be in 2-player games, which is also always very fun. Okay, let's suppose SpongeBob and Patrick plays a game. Okay, SpongeBob will start. And he can shade either 1 or 2 squares of a, this is 2x9 board. Alright, and the player that can no longer shade any square and loses. Okay. And we want to know whether there is a possible winning strategy. same place. Yes, they have to be next to each other. No, they actually don't. Make it any two shades, any two squares.
I'd say the strategy would be for player 2, and what they should do is, whatever player 1, whatever the number of blocks of player 1 shades, they shade that the same number of blocks.
Okay, does it matter where they shade these blocks?
No.
Okay, so did you say they can just shade anywhere? Okay, let's draw this quickly. Okay. So you just say if player 1 shades there, you just shade 1 block anywhere. Okay. Would that necessarily, is there a reason why it would definitely make you win?
So you shade, the reason why you shade the same number of blocks that they shade is because in that way, since you're player 2, if you shade the same number of blocks that they shade, then the number of blocks that can still be shaded will always decrease by a multiple of 2. And in that way, since the board is the number of blocks on the board is a multiple of 2, in that way, player 1 will, player 2 will always be able to choose the last, or always shade the last 2 blocks.
If there is a last 2 blocks. I'm not completely convinced yet, but we can look into it. You're at the back, yes.
I have my own strategy and a contradiction for each strategy.
Right.
So if player 1 keep playing 2 squares, then player 2 will also have to keep playing 2 squares, and that will go to 4, 1, and 8, then 12, and 16. And then there's only 2 left for player 1 to win. And then my strategy is always make sure after you play there's an odd number of squares left. So let's say once you get to like 5 squares left, then the other person will play, if they play 1, there'll be 4 and you play, so there's 3. If they play 2, you play, so there's 3, I don't know, how much is it? 3. And then they'll play, they can either play 1 or 2, so there'll either be 2 or 1 left and you can win. Probably wrong.
But it's a great shot.
Is
you can
that
definitely
always going to be 2 or 1 left? So,
at a point, sure.
so doesn't that? Okay. You don't know who's going to end up with that.
Let's try another strategy. Yes.
Player 1 can always win if he starts off by shading the 2 first blocks, and then he always makes sure there's an even. So then it's a 2 by 8, so then he would go last if you always make sure that there's an even number of squares. Then to player 1 plays 1 square, then he would play 1. Player 2
Plays 2, then 2. I'll have to think about that one. I think you win X.
I think player 2 can always win.
Okay.
If he matches, if he gets the piece after player 1 to 3, because 18 can be in a 2 by 9 board, it can be divided by 3 every time. So if he matches, whenever the guy puts 2, he puts 1. Whenever the first guy puts 1, he puts 2. In the end, he'll have the last square.
Yeah, that will work.
That might. Yes. Let's hear all
To
of
what he said, but if the first player colors in the 2 middle ones in the row, and then he just like does a mirror image of what the second player does. Then you can always win.
So the 2 middle ones would be these, right?
Yeah.
So you
And he
say
just does like a mirror image or the opposite of what the
they want to do that. And then if player 2 makes a square here, then player 1 should
On the opposite side.
make a square there. Why would this guarantee you win?
Because you'll always get the last one.
Okay, so it means if player 2 can color a square, player 1 can color a square, because you're making a symmetric move by dividing that basically in 2 parts. If player 2 would shade here, you'd shade there. It means as long as player 2 can play, player 1 can also play.
What if player 2 blocks you by playing on both sides?
Then you play on both sides. So player 2 does there and there. Oh, that does make it weird. Yeah, we're taking it back to you can only color one square, because this stops our argument.
But then you just go
can still
up,
work.
you can go on the
At the bottom. Or, well, the bottom's not necessarily open.
Both again, so they're not playing the exact same move as the other way.
But you have no guarantee that the other squares are not taken. So the argument is, as long as he has a move to make, you have a move to make on the other side, because you copied every single move he made. Right. Yes?
I think it doesn't really matter where you play, only matters the amount of squares to the left for you to play. And I agree with the other guy said earlier, there always has to be an odd amount of squares. Because if there's an odd amount of squares, whatever he plays, you will always have moves left. If there's 5, if he plays 1, you can play, then there's 4 squares left. You can play 1, then you could,
Yeah, so maybe.
yeah, and then he has to play 1 or 2. Then you get 2 or 1, so you win. So whatever.
whoever's move results in 3 spaces left is the winner. Because
Yes.
then they have to move and then you get to do the last move.
Yes. Yes. No, that's true. Go right up a proof and we can see how good it goes. But there was a lot of great suggestions, and I'm pretty sure a few of them will definitely work out. But really, try writing them up, and then we can check them all out. We just don't have enough time. There's some more examples to go through, but I really liked a lot of them. Okay, just let's see. Okay, now the last one. The time runs out. Okay. Oh, this is not good. Okay. Okay. Any suggestions so far? Any ideas? So the idea is you want to get, sorry, that handwriting's a bit bad. The idea is you want to get something that is constant in a way, that you could use, or something the one player can copy. Okay, at the front first.
I think that you, I don't know if we would have the winning strategy, but I think it could work along the lines of 2019 being a multiple of 3, and that you can always make a multiple of 3 using 2 of those numbers. Of 1, 2, 3, 4, 5.
Okay. Is it a multiple of 3 you can make from them? Yeah. So it's, in a sense, what do you want to do with those numbers to get a multiple of 3?
Like if they take, say, 2 away, then you could take either 1 or 4 away to get a multiple of 3 to make that 2.
Okay, that's an interesting observation. Let's try you at the back as well.
I think whoever makes the other person make it 2014, they win.
Okay.
Because then you can just take 5
And then you're there.
maybe you can pressure them by some.
Just pressuring them. Yeah, just steal the whole jar and run away. Yeah, I mean, it's cookies. We're all probably going to do that. Okay. Yes, so what we used in the previous example, although there was a lot of good examples about getting to 3 and seeing how that works, is we copied the other player. In a sense, we did a symmetry argument of copying what they did to the other side. And in 2-player games, that's something that comes up a lot, is the idea of copying the other player or the player before you. In this case, directly copying, if he takes 1, you take 1. If he takes 2, you take 2. That's not helpful in many ways. You can in no way guarantee you're going to win. But the observation he had is that you get to a multiple of 3. 2 plus 1 gives you 3. There's a lot of option every time to get those numbers to a multiple of 3. Or more specifically, what he said is, if you have 2, you can either have 1 or 4. But if you had 4, you get to 6. Similarly, if you have 5, you add 1 and you get to 6. If you have 3 and you add 3, you get to 6. The nice thing about that, yes.
I want to say that John can always win.
Okay, that is true. John can always win.
But I also think I have the strategy.
Okay.
So John should take 3 first, and then after that, he must take their move, minus from 6, and take that menu from the jar.
Okay, great. So why would you minus it from 6?
Because 2019, say like, if you divide by 6, there's always a model, and there's the remainder of 3, so that's why you should take 3 first, and every single time you minus 6, you'll get close, I don't know, it will get to 0 eventually.
Okay, at the back, yes? Oh, no, that's you. Sorry. Yeah, yes.
So then can't that be cancelled out by the other person just outright, instead of going 3, they... Oh, no. No, but then you can just do like a big number that goes over the amount that... Okay,
The biggest number you can do is 5. So, okay.
Does it really matter what happens in the initial stages?
Not always, but
once you get in sight of 2019, let's say within 10,
it's
the strategy. How much does it matter what has happened up until that point?
Well, if you have two players and the one, as we're going to see now, has a winning strategy, the winning strategy comes from what he did in his first move. And then because his first move, and then from there, he basically kind of repeated certain steps to kind of stay in the same pattern until you get to 2019, which means for the second player, when you get close to 2019, he can't do anything to break this pattern because he can't change the other one's move. So in this case, it definitely is what the player did first that makes him win. Okay, let's start that corner.
I was
Yes.
just going to say, because otherwise, player 2 can take it. If player 1 doesn't make sure that there's always a multiple of 3 left, or multiple, 3 or 6 left,
Mhm.
then player 2 can do that.
Okay, yes, yes, exactly.
I think it's only
That's
multiple of
actually-
6, not the multiple of 3. Because it doesn't matter if it's multiple of 3. If it's under 6, the player whose turn it is can win.
So it's actually going to be a remainder of 3 left, but we're going to count in multiples of 6. Any other? Yes?
Yeah, I was just going to say that it's important that he keeps up this pattern from start to finish. Otherwise, if he messes up and takes the wrong number of cookies, then player 2, if they're smart enough and know what to do, then they can start doing the same thing that player 1 was doing, and then player 1 can't do anything to stop player 2 unless player 2 messes up.
Exactly. But in this case, we are going with their optimal players, and they're playing precisely according to the strategy we tell them to. But that is a very good point. They need to keep with the strategy the whole game.
So isn't it basically the person who gets the amount of cookies taken away to 2013 wins? Because if the other person goes anywhere from 1 to 5, it will be anywhere from 2014 to 2018 and the other year.
Yes, that's also true. That's kind of how you can take the winning position and you can pinpoint it to a lot of different. So you can, in the very initial stages, say basically the one that already took 3 cookies and doesn't have to play first now is already the winner. So as he said, we're going to focus. He said multiples of 3 and multiples of 6. Why multiples of 3 doesn't work is because if the other player, or not multiples of only 3, as in if the other player picks 4, you can't do anything to make sure that the sum of the cookies you take is equal to 3 because you already overshot that. Yes?
Can't you do plus 5, so it's 3 3s?
So
Instead of
you
being
can
a
go.
6, it's a 3.
Well, yes, it's not. So it's another multiple of 3, but you can't. You need one number that you can always get to, and you can't always get to 9. For instance, if he takes 1, you can't take 8. Yes.
I'm saying so let's say you keep going 3, then if you go to 9, that's basically jumping a whole turn. You just get rid of that
Or you
turn.
skipped a whole.
And instead of going 3 at 6, you just go 9.
Yes, but then it's the other player's turn in the next round. So it's not that you both played and that was a 6. You just skipped till 9, and then it's the other player's turn, which could be problematic for you because he can steal your strategy at that point. Okay, so why 6 is ideal is because with these numbers, it's the only multiple of 3 that you can always get to with those numbers, irrelevant of what the other player did. So if he played 1, you play 5. If he played 2, you play 4. If he played 3, you play 3. So the sum of the move that both of you made together now is 6. Why this is ideal is because it means that every time the other player plays and then you play, your moves together, you reduce the number of cookies in the jar by 6. So your both turns as a set reduces it by 6, and then by 6 again, and then by 6 again, by 6 again. And you can make sure this happens that way. But now we need to check how is 6 related to 2019 and which player will win, because obviously a player needs to start. And if you want to copy the other player's move, but you're the player that starts, that's not going to work very ideally. Let's see. 2019, it turns out, is equal to, 36 something times 6, which is 2016 plus 3. Okay, so that you're just gonna jam out and find that. Okay, so what we see is we don't really care about this number specifically. We just care that 6, it goes into 2016, and then we have this remainder of 3. And this is, again, mods is great stuff. I mean, okay, the remainder of 3. Which means that if you're counting up in multiples of 6, and you start from the start, you're going to get to 2016 at a point, and then there's going to be 3 cookies left. So if you're player 1, yes?
Then can't player 1 at the start just do 3.
Exactly. So we're not going to do the 3 at the end, we're going to do the 3 at the start. Because we want player 1, or we want a player to copy the other player, right? So, but player 1 can't copy player 2 if player 1 obviously starts. So that's why we're going to do this 3 at the start. Because in this sense, we want player 1 to copy player 2, but player 1 starts. But let's say player 2 copies player 1, and we're thinking, hey, player 2 might actually win. Then player 2 is going to copy player 1 all the way till 2016. But then player 1 is going to take the last 3 and win. Which doesn't work, because player 2 is then playing our optimal strategy, but player 1 wins. And that's how we know we need player 1 to take this 3 at the start, so that it then starts from player 2 playing first, and then player 1, so that player 1 can copy player 2 the rest of the game. Okay, any other questions regarding this? Okay, I think that is the time. So, yes. Thank you guys, you really had a lot of great ideas. I really think it makes a difference.